In this video, you're going to learn about work, energy, power, introduction. Do not forget to like and subscribe my YouTube channel. So let's proceed. What is work? Work is actually any activity that requires muscular or mental effort. Theoretically, in physics, work could be expressed as W equal to F times S, or the product of force and displacement. So we have the following units for your force, displacement, and work. Your force now is newtons in MKS or SI, CGS as dynes, and pounds for FPS. And then for the displacement, we have your meter for MKS or SI, centimeter for CGS, and feet for FPS or English. Then we have your work here. Work is equal to 1 joule or 1 newton meter for MKS or SI, 1 erg or 1 dyne centimeter for CGS, and feet pound force for English or FPS. Now, if you're going to consider these diagrams for the first one, okay, the upper portion diagram, we have your block here, mass M with force as push or pull applied towards the block, okay? So the block is moved from point here to here with a distance or displacement of S, okay? To calculate now the work is equal to F multiply it with D or displacement. Now, if we're going to consider the second one here, your block of mass M, a force is applied with an angle theta, okay? So the block here is moved from this point of view up to this point, okay, with a displacement of S. So if we're going to consider now the force, okay, we're going to calculate it through the force component with respect to the horizontal. So say, for example, the angle between your f of x here, okay, or force horizontal as denoted by this broken arrow or broken line, okay, pointing towards your right, okay, then an angle between your f and your horizontal force here. To get now your horizontal force here would be, this is your adjacent and this is your hypotenuse. So horizontal force now would be equal to F cosine of your whatever angle given here as theta. So to calculate now the work gives us F cosine theta. This is your horizontal component of force. Multiply it with the distance or displacement D. Now for a block, okay, being pushed or pulled in an inclined plane, we're going to consider the following. The quantity here is actually the summation of forces with respect to the x-axis or inclined x-axis here, okay? Inclined x-axis, okay? So what are the forces affecting the inclined x-axis? So we have the friction, okay? And then the force applied, as well as the um, inclined horizontal or inclined x-axis of your weight as WH. So we're going to call to get the WH here. Okay. So since this is theta, and then trigonometrically, this is also theta or whatever angle here is equal to the angle here. Okay. So we're going to get now the WH. So since this is the opposite and then your W here is the hypotenuse, okay, this could be expressed as WH is equal to W sine of theta or whatever angle is here or here. Now, to determine the um, inclined force here, okay, summation of the forces, okay, on this inclination or summation of forces with respect to the inclined horizontal axis or inclined x-axis would be equal to, since your force here is points towards your right, okay? So let's denote this as positive and then your the WH, or the horizontal axis for your weight, points towards your left, so minus. So to get now the summation of forces with respect to this inclined x-axis gives us F minus W sine theta, okay? And then this quantity is multiply it with the amount of displacement, okay? So the second image here, okay, lower image here, we have your angles expressed with respect to your displacement and force. Now, if the displacement is the same with the direction of the force applied, the angle makes by the both gives us 0 degrees. Now, if the force, okay, is applied opposite to the displacement, the angle here is 180 degrees. Now, if the force is applied upwards, but the displacement is going to the right or left, the angle can be expressed as 90 degrees. If the force is applied upwards and the displacement is upwards, the angle here is 0 degrees. Okay? If the force is applied at an angle, say for example, we have this one as 45 degrees, which is subtended with the force and the displacement. As you can see here on the example, we have a man, okay, applying force on a lawn mower with an angle theta with respect to the horizontal displacement. So to get now the work done would be equal to force multiplied with cosine theta. Then the whole quantity is multiplied with the amount of displacement. Here, as you can see, the displacement here is 0. Okay, so work done here is 0. Why? Because he is just stationary. Only the force is exerted on carrying the suitcase. But if he starts to walk, okay, the force now is upwards because he is exerting force on carrying the suitcase. And then as he walks horizontally, this is your displacement. So upward force and displacement pointing towards your right, the angle between the lines would be 90 degrees, okay? So cosine of 90 degrees gives us your 0. And then we have your example here, okay? Your fourth example as a suitcase is being carried with the amount of force F, okay? Walking upwards in displacement diagonally upwards on a staircase, okay? So we're going to get now the amount of work. Work now is still equal to F cosine theta multiplied with the displacement. Now, how about this one? We have, say, for example, a man carrying a suitcase in an elevator. Okay. So we have this electric generator. This pertains to the elevator. So the force is upwards and the displacement is downwards. So this angle is actually 270 degrees. Getting now the cosine of 270 degrees gives us 0. Okay. So the work here, since this is 0, but the displacement would be in terms of height. So there is still amount for the work. Now let's proceed with the second parameter as your energy. Energy is actually the ability to do work. So we have the first type of your energy. We have the potential energy or PE. PE now would be equal to the products of the following parameters: mass, gravity, and height. Okay. Then we have the third one as your kinetic energy. Okay. So for example, this one. We have a block with mass m and applied force, either pushing or pulling the block towards this distance d of displacement going to this second point. Okay. Prior pushing or pulling the block gives us an initial velocity of 0. And then during pushing or pulling the block to this place gives us an acceleration and a final velocity of v1. Now, the work done on a body on this diagram is equal to the kinetic energy or change in kinetic energy. Why is it change in kinetic energy? Because you're going to consider two velocities there. We have your final velocity and initial velocity. Now, work is equal to force times distance. We're going to expand your force, that is force would be equal to mass times acceleration. And then we have these following quantities here. We have your twice of acceleration multiplied with S. S denotes here the displacement could be D as well. So it is equal to your final velocity squared minus initial velocity squared. If we're going to further simplify this gives us your acceleration times your distance would be equal to your final velocity squared minus initial velocity squared all over 2. So delta kinetic energy is equal to mass times acceleration times the displacement S or D. Okay, so delta KE is equal to MAS or M multiply it with final velocity squared minus initial velocity squared all over 2. Okay, so this gives us, if we're going to distribute your mass on each terms as half of mass times final velocity squared minus half of mass times initial velocity squared. So since in this example or diagram, the force exerted start at rest, okay? So when we say at rest, your initial velocity V sub O or V sub I would be equal to 0. Hence, simplifying this equation gives us delta KE multiply it with half of mass times final velocity squared for this example. Okay. Then we have the law of conservation of energy. Law of conservation of energy states that energy is neither created nor destroyed, but could be converted from one form to the other. Okay. Say for example, we have your light bulb from electrical energy produces light energy and radiant energy. And then after using at a certain point in time, your light bulb could be converted to heat. Okay. And then stored electrical energy if you turn off the bulb. Kinetic energy for a high-speed particle, this is proposed by our scientist Sir Albert Einstein, as kinetic energy is equal to mc squared. Okay, c here denotes the speed of light. Okay, so m sub o c squared or initial mass of the particle multiply it with the speed of light is equal to the rest energy, and then we have the final amount of mass of the particle multiply it with the amount of speed of light squared. This is equal to the total energy. So energy, okay, kinetic energy of a particle is equal to mc squared. Now let's proceed with the third quantity. We have your power. Power now is actually the rate of doing work or work all over time, okay? When we say rate, that is per unit of time. So say for example, we have power, so this is the rate of doing work or work per unit time. So P now is equal to W all over T, but W is equal to force times distance. P is equal to force times distance all over T, but V is equal to D all over T, or your velocity is equal to distance all over time. If we're going to further substitute this gives us a force times velocity. The D all over T here is actually your velocity, okay? Where P again is equal to the power, F is equal to the force, V is equal to the velocity, and T is equal to time. And W is equal to your work. Now, the following, we have the units, okay? For your work in SIMKS, that is in joules, CGS, that would be in ergs or centimeter grams per second. Okay? And then for English or FPS, we have feet pound force for your work. Then we have your force that is newtons in MKS or CGS, and then we have dynes for CGS and pound force, okay? The pounds here is actually pound force. Please do not be confused with pound mass, okay? For force, that is pound force in English or FPS. And then we have the velocity in meters per second for SI or MKS. And then we have centimeter per second for CGS and feet per second for FPS or English. And then for the time, okay, it's units. We have seconds for MKS, CGS, and FPS respectively. And then we have for the power as 1 watt would be equal to 1 joule per second for MKS and SI units, and then ergs per second for CGS. Then we have feet pound force per second for FPS. Now we have the conversion, as 1 horsepower HP is equal to 746 watt or 550 feet-pound per second. Okay, so that concludes my presentation for the introduction of work, energy, and power. For my next video, we're going to proceed with work, energy, power, sample calculations. For further questions, you may inbox me through my messenger account or our LMS inbox. Have a nice day. Thank you very much for listening.